Ladies and gentlemen, welcome, a virtual welcome to the Institute of Advanced Study at the University of Amsterdam. My name is Peter Sloot. Today is a special day in many ways. Today is special as it's the World Science Day for Peace and Development, as proclaimed by the UNESCO in 2001, to be celebrated each year on the 10th of November. Today is also special as the Institute for Advanced Study here at the University of Amsterdam kickstarts an ambitious series of lectures under the name Science Beyond the Horizon, where world-renowned scientists open up new vistas to radical new ideas in science and technology. Ideas that may be dreams now, but that potentially become real in the future. For this, the Institute of Advanced Study invites what we call competent rebels. Competent rebels to show us the way to the future. And finally, today is special as we have Professor Stephen Wolfram to open up this series of Science Beyond the Horizon. The agenda is that we will first have our moderator, Professor Sonja Bais, to introduce Stephen Wolfram, and then we will have 15 minutes of lecture by Stephen. After that, we will have a panel of 4 experts to pose questions to Professor Wolfram. If you have some questions for Stephen or for the organization, please do so via chat, via the chat box that we have in Zoom. We will gather that information and plan to get back to you as soon as possible. Having said this, now I would like to invite Sonja Bais to introduce Professor Stephen Wolfram. Sonja, the floor is yours.
Thank you, Peter. It's a great pleasure and honor to introduce Stephen Wolfram, who is a distinguished scientist who has been extremely active in the fields of physics, mathematics, and computation. He is a very innovative thinker, I would say, fearless researcher who has in all the time, has opened up novel fields of inquiry. Stephen Wolfram started as a boy, basically, studying physics at Oxford University, and then moved on to Caltech in Pasadena, California, where he obtained a PhD in theoretical particle physics in 1980, at the age of 20. Yes, 20, okay. The year after, he received a very prestigious MacArthur Fellowship. This is a huge grant awarded to really outstanding and very creative young researchers. He was one. He is one. He moved from there to the Institute for Advanced Study in Princeton. And along the way, with this grant where he could really study whatever he thought was of relevance, he started moving away a little bit from physics in the direction of computer science. So while in Princeton, he started developing these symbolic manipulation programs. First, there was a program called SMP, Symbolic Manipulation Program, and later he developed from that a magnificent piece of software, a huge programming environment called Mathematica, a program that just does mathematics on the graduate student level and is very versatile. This has become an indispensable tool for researchers, for scientists, engineers, and students all over the world. He moved from the Institute to the University of Illinois in Urbana-Champaign, where he founded an Institute for Complexity Science, but also in 1986 founded his company, Wolfram Research, a very successful company of which he is, or has been all the time, the CEO. And this company, of course, runs, distributes, maintains Mathematica, but later on it also developed other great software tools. like Wolfram Language and Wolfram Alpha. Wolfram Alpha is, say, a real knowledge base. It's an interactive repository of knowledge. It's a question-answer machine of some sort. These are very impressive new tools used by a lot of people, like myself. Moving in and working on this computation, and maybe thanks to that, I think Stephen Wolfram developed a different perspective on the whole enterprise of science. He moved his perspective from, say, what we usually say is, say, that mathematics, like calculus, algebra, geometry, is the true fundamental language of science, of nature. And he moved from there to a different perspective in which computation and information are the central ingredients of a fundamental way to build a theory of science. So he developed those ideas. And maybe the simplest way to say it is he discovered that if you start with very simple programs and rules and you run them for some time, then structures emerge which will exhibit an extreme complexity, a complexity that you cannot immediately understand by the usual mathematical techniques. So this was all led to, it worked out in great detail and in great extension in a beautiful book. This is the first book, A New Kind of Science, which is really based on this idea, and it is richly illustrated. And you see, it is a Bible-sized scientific bestseller. Now, this brings me to our program tonight. And we are, of course, honored that Professor Wolfram will be speaking to us about a new book that has come out this year, a project to find the fundamental theory of physics. A project to find. So this is a project, that is a description of a project. And it goes a little bit along, it builds on, more versatile, simple programs are studied. And yes, then the question becomes, is the structures one achieves, they are very complex, and maybe they have something to do with reality as we know it, the world we happen to live in. So the questions are then, and hopefully he will go into depth on that, can you recover fundamental principles from the sciences as we know them, like causality, the theory of relativity for space and time, the quantum theory of matter and radiation, evolutionary biology? These questions, can you extract them from or recognize them in these structures? So this is a huge project. It's a project that I see is also very well represented on the web, and people, I think, can join that even. I certainly recommend that. So yes, I look forward to a very, very, very interesting lecture. And I think, as was mentioned, we will have a panel discussion afterwards. I will, after the lecture, introduce the members of the panel. But for now, I would like to invite Professor Wolfram to take this virtual floor and deliver his lecture. Professor Wolfram.
Great. Thanks very much. Thanks for a very, very nice, interesting introduction. So I want to try and tell you a little bit about a thing that has been a great surprise to me over the last couple of years, which has been that this kind of big paradigm of computation that I've been working on for 40 years now seems to be delivering to us a good story for how our universe works, for a theory of fundamental physics. So the main thing I want to do is tell you a bit about that, but I also want to give you a little bit of the background, a little bit of the consequences of a success in this computational paradigm for fundamental physics. So maybe I should start a little bit at the beginning. As Sander mentioned here, I started life as a physicist, an ordinary physicist, like particle physics, cosmology physicist. But I ended up building computational tools to sort of help me with things I wanted to do in physics. But that led me to try to understand more about sort of the foundations of computation, and to try to understand sort of what are the fundamental primitives of computational processes. But then I got to thinking, okay, let me try to see what I can do in modeling things in the natural world. Can I use the kind of methods that I know from physics, or are they going to get stuck? And what I found, this was beginning of the 1980s, is that when I wanted to study systems where the behavior was quite complex, things in maybe physics, you know, fluid turbulence, something like that, biology, whatever else, I found that the methods that I knew from physics, you know, solving partial differential equations, things like that, just didn't seem to go the distance in being able to understand what was happening in these natural systems that showed complex behavior. So I got to thinking, okay, could we take this idea that had been so successful over the last 300 years of making essentially a formal model for a system in nature, and could we generalize that idea? And the idea for like 300 years had been, let's use mathematical equations to make those underlying models for the natural world. So the question is, can you generalize beyond that? And what does it look like when you generalize beyond that? And the thing to realize is, if we believe there's a model of things, there's got to be some definite rule that says something about how the system behaves. The question is, what is the most general sort of source for those kinds of rules? And what I realized is, these things that I'd studied from the foundations of computation, they are a more general source of possible rules for systems than the kinds of things that we happen to have studied in mathematics with calculus and things like this. So then that led me to the question of, okay, so let's say that our world is basically modeled, represented by programs. What kinds of programs might they be? Are they the kinds of programs that we would typically write for some particular human purpose that might be, you know, thousands, millions of lines long? Or are they instead very simple programs that we might just sort of find if we were randomly to enumerate possible programs? So it got me started in something which was sort of, okay, so what do simple programs out there in the computational universe of possible programs, what do simple programs typically do? And that's a question that one can think about it, and one can think, oh, a program that's sufficiently simple, it must do very simple things. But it was easy enough for me to do it, so I kind of was able to kind of turn a computational telescope to this computational universe and just do the experiment and find out what's out there in the computational universe. So let me show you perhaps kind of a modern version of that, that experiment. Okay, that's a prelude of other things I'll show, but let's start with something different here. So the system let's see, I probably should make this a bit bigger. The kind of the easiest to understand what's going on systems that I found with these things called cellular automata. And the idea of a cellular automaton is you just have a line of black and white cells, and at every step, the color of a cell is determined by the color of its two neighbors on the previous step. That's the sort of simplest case of a cellular automaton. So this is a particular rule which says, you know, if you see a black cell in the middle, two white cells on either side, you make the cell in the middle black. Okay, so now let's say we take that rule and we say, let's make a picture of what that rule does. Let's just run that rule starting, we could do that one too, but let's run that rule starting from just a single black cell. Let's run it for 40 steps, and let's say, let's just run that. Okay, so this particular rule, very simple rule. We started off from one black cell at the top, very simple behavior. It's kind of like that's what we would expect would happen. Okay, let's change the rule a bit. Let's say we pick this rule instead. Let's run that rule. Okay, a little bit more complicated, makes a checkerboard pattern, but again, simple rule, simple behavior, kind of what we might expect. Let's try one other example. Let's try this rule here. Let's run this one. Okay, that's a little bit more elaborate. Let's try running it a bit longer. Okay, let's run it for 400 steps. Okay, that's what we get. So very simple rule here. The pattern we get is very intricate, although we can still see that it's somehow fundamentally very regular. We somehow are not terribly surprised if we saw a pattern like this, that it's generated from some very simple underlying rule. Okay, well, let's just try doing sort of a systematic experiment. Let's just take all possible rules. There are 256 rules of this simplest kind. There's 2 to the 8 cases here. Let's just make a picture that shows for each of those rules, let's just show what it does for, let's say, 40 steps. And so we can just do this, okay, n from 0 to 255. Let's just run that and see what it does. So in each case where each of these images is a different rule, many rules, what happens is very trivial. You just start off with one black cell here, it goes off to the left. Whatever else, here we've got a nested pattern. These are just making stripes of various kinds. Okay, we keep going, we keep going, we keep going. Aha, okay, so by the time we get to this one, this is rule 30 and this enumeration, this is kind of my all-time favorite science discovery. This is kind of the computational universe analog of turn your telescope to the sky and see moons of Jupiter or something. It's something really quite surprising that, at least for me, I completely did not expect was there. So let's understand what this rule 30 thing is. Let's look at its rule up here. Okay, there's the rule. It's just one of these things that says the color of a cell based on the colors of neighboring cells and so on. But let's run it for 400 steps, see what it does. Okay, this is, to me, a very remarkable sort of intuition-breaking thing, that it's possible from such a simple rule to get such complex behavior. There's a certain amount of regularity you can see over on the left here, but if you look at, for example, the center column of cells here, for all practical purposes, it seems completely random. It's random enough we've been using it as a pseudorandom generator in Wolfram language for a long time, and it's kind of one of the most robust known pseudorandom generator, actually. But this is coming just from this very simple rule. It seems very much not what one's intuition would suggest. I mean, our intuition, based on doing things like engineering, is if you want to make something complicated, you have to go to lots of trouble, you have to have a very elaborate plan, et cetera, et cetera, et cetera. But this is something different. It seems like in the computational universe, if you just pick simple rules almost at random, you'll quite quickly start finding ones where they produce immense complexity of behavior. And one of the things that I kind of realized and that got me really excited about these kinds of things is one's always been very curious in nature. It seems like there's lots of complexity produced all over the place. What is its cause? What is the fundamental reason that nature is able to make this kind of complexity? And what I realized is that, in a sense, what we're seeing in the computational universe seems to be a lot to do with what the sort of secret that nature has that allows it to make all this complexity. That in this computational universe, if you don't constrain yourself to only deal with rules of the kind that we've typically used in engineering, where you can sort of readily foresee what's going to happen when you run the rule, if you don't constrain yourself in that way, it's actually very easy to find rules where you have immense complexity of behavior. Okay, so one question then is, what's the broader scientific context of thinking about what's going on here? And I think the important thing, when you study the computational universe, you find this kind of complexity of behavior is quite common. So the question then is what does that mean? So I think the way to think about it is in terms of this idea of computation. You think about the process that's going on here as being a computation. You're starting off from some initial state, then the system, but with this kind of machine code rule, is computing what will happen in this particular in the particular system as it goes forward. And you can think of that as a computation. So then the question is, how sophisticated is this computation? Is it a computation that is something that is a fairly simple computation, or is it some computation that's much more sophisticated? So one of the things that's sort of been the most overarching principle that I've derived from lots of studying the computational universe is this thing I call the principle of computational equivalence. And what that says is, as soon as you see a system whose behavior is not obviously simple, it will correspond to a computation that is of maximal sophistication. So as you kind of increase the complexity of the rules, there's suddenly a threshold above which basically you can start seeing behavior that corresponds to a computation that's as sophisticated as anything. Okay, so what are some implications of this principle of computational equivalence? So one implication is that it should be the case that these systems can be universal computers. That is, that, but before the 1930s, people had kind of assumed if you want to do a different kind of computation, you need to get a different piece of computer hardware to do it. But then from Turing machines and other things, it was realized that no, that's not the case. You can have a fixed underlying machine code, so to speak, but just by giving different programs, you can do different computations. But then the question is, how sophisticated does that underlying system, does that machine code have to be in order for you to be able to support universal computation? And what the principle of computational equivalence says is that actually as soon as you see behavior in the computational universe that isn't obviously simple, you will reach this point where, among other things, you see universal computation. We don't know for sure yet for Rule 30 that it's computation universal. We do know for Rule 110, which is another rule of this type, that this is capable of universal computation. We can sort of see it actually here, probably, it only goes on the left-hand side, but we can see it here, producing these little structures that show different kinds of things going on, and you can kind of imagine them as little particles that interact and can do sort of logic operations, and yes, you can show that that really works. And over the years, there's been more and more evidence for this principle of computational equivalence. In fact, I'm just right now on the hunt for a new piece of evidence that's going to be rather cool that hopefully I'll have in a couple of weeks. But another piece of evidence came from in Turing machines, sort of the center of kind of thinking about theoretical computation. There's the question of if you just enumerate possible Turing machines, eventually you get to one. This is the very simplest one that doesn't show obviously simple behavior. And a number of years ago, I put up this prize for somebody to show whether it was universal or not. And indeed, it turns out to be universal. And that's kind of another piece of evidence for this principle of computational equivalence. So what are the other implications of the principle of computational equivalence? Well, another one that's important and that will come back in some of the rest of what I'll talk about is a phenomenon I call computational irreducibility. So the question is, how can you predict what's going to happen in this Rule 30 system? The thing that's been sort of a big triumph of traditional exact science has been, yes, we can predict what's going to happen. In other words, the system does its thing. The Earth goes around 1 million orbits. But we can have some formula, essentially, that much more quickly than just following all those 1 million orbits lets us figure out where the Earth is going to be 1 million years from now. And this idea of being able to sort of jump ahead and computationally reduce what's going on by being sort of smarter than the system, be able to figure out what the system is going to do much more efficiently than the system itself does it. That's kind of the computational reducibility is the core of a lot of what people have thought is valuable in traditional exact science. The question is, does this system show computational reducibility? Well, I don't think it does. I think if you want to work out what's going to happen, for example, on the center column of cells, if you want to work it out 1 million steps from now, you pretty much just have to follow 1 million steps in the evolution of the cellular automaton to find out what it's going to do. So how would it fail to be that that was the case? Well, okay, so this relates back to this principle of computational equivalence. If what we would have to do, if we were going to outsmart Rule 30, that means that we, our brains, our computers, our mathematics, whatever, essentially have to be doing more sophisticated computations than Rule 30 is doing. But this principle of computational equivalence says that that's not the way it is. It says that instead, we are all equivalent in the sophistication of computations we can do. And that's why, in effect, the behavior of this system seems to us computationally irreducible, because we are not capable of any more sophisticated computation than it is. So to know what it's going to do, we essentially just have to simulate it and find out what's going to happen. And that's a very important idea. I think it has many, many, many consequences that range from consequences for science to consequences for AI ethics to consequences for all kinds of different things, to helping us understand how phenomena like free will arise from deterministic systems, these kinds of things. But we can also ask it at a sort of more mathematical level. We can say, okay, let's imagine we have something like this Rule 110 system. Say, what's it going to do? Are these structures going to last forever, or are they eventually going to die out? What's going to be the infinite time behavior of these systems? Well, if there's computational irreducibility, the only way we answer that infinite time question is to run it for an infinite time. And so effectively, this becomes something, if there is computational irreducibility, this becomes something that we have to consider undecidable. What's it eventually going to do? You know, we can't tell what it's going to do. You know, I know if I run this, I think it's about 3,000 steps I have to run it. If I run it for 3,000 steps, finally you'll see that it's sort of resolved in this particular case, and you can see what it's going to do. But there's no a priori upper bound on how long you have to run this for in order to determine what it's going to eventually do. So, okay, so that's sort of the story of computational reducibility, kind of the story of what you see in the computational universe. And there are many, many consequences of all of this. I mean, one of the important things is that by looking, in a sense, what we're seeing is there's a lot of rich and complex behavior in the computational universe. What can we do with it? Well, one thing we can do with it is we can kind of mine it to make models of actual systems in the world. And one of the things I've always found amusing is that my 256, elementary cellular automaton rules, I used to actually keep physical file folders of, papers that came out that were using rule 18, rule 22, rule 184, whatever, for different applications. And it's been really quite interesting to see that these models, they're sort of very minimal models. And so in a sense, it's not surprising, but it's kind of interesting that over the years, almost every one of these rules has been used as, a model of catalysis, a model of road traffic flow, a model of something else. They're raw material for making models of things, and that's a general feature of the computational universe. A thing that I think is a really very dramatic phenomenon, although as is usual in sort of the history of science, when you're in the middle of it, it's hard to tell it's even going on. But if we look at the history of science and the history of sort of the exact sciences, for about 300 years, kind of mathematical models, mathematical equations and so on, were the foundational raw material for basically all models that got made of things, all exact models that got made of things. In the last probably 15, 20 years, there's been this transition that new models that get made are almost always program-based models, not mathematics-based models. And it's sort of it's kind of a very interesting shift to see after such a long period of time. And once you are dealing with these computationally based models, there are many different kinds of phenomena, like computational irreducibility becomes a core phenomenon that you have to deal with, and there are many kinds of things like that. I might just say that I'm going to talk about kind of a big application of computational models in a few minutes, but let me just say a few things about kind of how to think about this kind of computational universe and its role and so on. So one of the other things that one can do with the computational universe, instead of, as well as mining it for models of the world, we can also mine it for things that are useful for technology. So I mentioned, for example, that Rule 30, for instance, is a useful thing as being a random number generator. But the question is, if we pick some technological goal, can we go out into the computational universe and find some computational system that can be useful for that particular goal? It's very similar to what we see in the natural world. We go out and we find, magnetic materials and we discover that they're useful for making compasses, or we find liquid crystals, we find out they're useful for making displays, things like that. This is the same kind of thing, but applied to the computational universe. Can we go out into this computational universe of possibilities and basically find things that are useful for our particular human purposes? Now, there are lots of things that go on in the computational universe where we see them, we might say, if we study these kinds of things, that's cool. It's like, but I don't know what it's good for. It's interesting, but I don't know what it's good for. In other words, our technology, our human goals have not really intersected with the things that particular system in the computational universe does. So I think one of the things that's sort of a great challenge is there's this kind of ocean of computational possibility out there in the computational universe. And then there's the set of things that we humans actually want to do. And the big sort of issue is to bridge that gap between what's possible in the computational universe and what we humans want to do. And I guess I can view it as I've spent a large fraction of my life trying to bridge that gap by trying to build kind of a computational language that allows us to express the things that we think about, that we want to think about, in computational enough terms that we can make use of what's possible in the computational universe to work out what we want. And so, as many of you will probably know, that whole story is the story of our whole Wolfram language system. And I just to say a couple of things about this, because I think it's perhaps interesting to understand. Kind of the goal here is to produce kind of a way of taking our thoughts and making them computational. To take, if you have something you say, I don't know, let's say, let's say we're talking about, countries in Europe or something. And we might then to take that thing and represent it computationally. And maybe we can say, let's do this. Let's say, let's try and get images of flags of countries in Europe, let's say. And then let's say we could take, I don't know, what should we do here? We could say, let's do this. Let's say we make, a feature space plot where we try and arrange these things by some machine learning method of, what looks like what or something. Or we could take, I don't know, we could take one of these and we could say, let's take that and let's edge detect it or something like this. The goal here is to be able to represent in this symbolic language the ways that we think about things, so that we can, among other things, get computers to help us do that thinking. And the other thing which I've realized increasingly is important is this computational language is a way of us having a notation for thinking computationally about things. I mean, I think historically, the analog is what happened with mathematical notation. I mean, if you go back more than 400 years ago, when people were talking about math, they were talking about it in terms of words. Then about 400 years ago, people started inventing time signs and equal signs and things like that. And suddenly it became much more systematic and streamlined to think mathematically. And that's what led to algebra and calculus and the mathematical sciences and so on. And in a sense, what I view us as trying to do in building this computational language of ours is it's sort of a unique effort to kind of build a full-scale computational language that can represent the world computationally and provide us essentially a computational notation for thinking about the world. And that computational notation, the hope is that just as mathematical notation led us to be sort of streamlined use of mathematics and led to the development of mathematical sciences, so similarly this kind of computational language can lead us increasingly to the development of the sort of computational X fields, where X is sort of any existing field from sort of archaeology to zoology. Okay, so the main point here is that in this sort of computational universe of possibilities, there's a lot of richness, and one of the challenges for us humans is to make use of it, and that's what our whole Wolfram language, computational language initiative is about, is how do you best make use of both what's out there in the computational universe and the kinds of knowledge that our civilization has accumulated. How do you bring those together, and how do you be able to best make use of that and best define a framework for people to think about things computationally? But one of the questions that you can ask then is, okay, we've got this idea that that there's sort of this computational universe of possibilities that provides raw material for models of things. Well, okay, let's think big. What's sort of the biggest thing that we might try to model? Well, the biggest thing is probably our universe. And the question then is, well, is there a way for us to use these kinds of ideas, these kinds of computational ideas, and find a model for our whole universe? And one's certainly encouraged, because you look at Rule 30 and you say there's a very, very simple rule. It does very complicated things. Maybe there's a similarly simple rule that governs our universe if we could just find the right one, and that will give us all the richness that we actually observe in our universe. What might that rule be like? Well, I started thinking about this. I was very pessimistic about the possibility of finding such a thing. And, it was like, well, let's think about cellular automata. Well, that's not going to work. It's as, the idea of having sort of a rigid arrangement of things in space and time is kind of something of a non-starter from what we know in 20th century physics. So in a sense, what one has to do is go below space and time, go below things like cellular automata, find a simpler foundation for what one might try to build the physics out of. And so I started looking at this in the 1990s, and it came up with a bunch of ideas about networks and so on, and actually made a lot of progress with that, and spent 100 pages writing about it in that big New Kind of Science book. I think it was kind of interesting, because the main thrust of that book is to talk about what you learn from studying the computational universe. And for me, physics was just one of the use cases. It wasn't really a central piece of the story. But I think, and so at the time, I think physicists were like, oh my gosh, this is so different from what we're doing. It's couldn't possibly be true. But in any case, I ended up not pursuing it much at that time. And then well, almost 20 years went by, and I worked on lots of kinds of other things, like Wolfram Language, like Wolfram Alpha, lots of things to do with understanding how to leverage this idea of computational language in the world and computational paradigm, but not in physics. And then a couple of years ago, I kind of made a little bit of a breakthrough in finding a sort of more elegant way to formulate kind of the underlying stuff that could be used to make computational models of fundamental physics. And then a couple of young physicists told me, you know, this whole idea is much too strong for you to just put it aside and let it languish. You know, you got to work on it and we'll help you do it. And so that got us started last fall, actually, just a little bit more than a year ago now, in a big effort to try and see just how far we could really get with these kinds of ideas. And actually, I think Jonathan Gorod is probably on the chat here. So he's one of those two physicists who's been working on this project. And if you have, I'm not going to go in terribly much technical detail here. And so he might be able to answer some of the more technical questions that come up. Okay, so let's say you're going to make a sort of a fundamental model of physics. What might it be like? Well, this is kind of a kind of an overall sketch of how this model is set up. But the first question is, what is the universe basically made of? And so one of the things that's sort of a very fundamental question is space. We imagine, you know, from Euclid on, we kind of imagine that space is just this background thing, and we can just say there's a coordinate, we can put it down any place in space. Space is a continuous thing, and so on. We might have thought the same thing about a fluid like water, you know, 150 years ago, 200 years ago, but actually we know that in the case of, for example, water, it's not a continuous thing. It seems continuous at a large scale, but on a small scale, it's a bunch of discrete molecules bouncing around. We haven't thought that about space because we haven't really been able to make that work somehow. People did think it at various different times, so one of the foundational things that we're doing is to imagine that space is not continuous. Space is made of sort of atoms of space. In a sense, what the universe is made of is a collection of discrete points. And those points are completely abstract things to begin with. They're just elements. The only thing that's true about them is they have an identity. Each one has an identity. So then how are these points related? Well, they're just relations between them. And there can be a relation of 3 points are related, 4 points are related, whatever. All we're doing is defining a collection of relations between points. Okay, so we can think about that at a more kind of formal level. That's like a graph or a hypergraph. If we were always pairing points together, that would be like a graph where we have an edge joining two nodes. But in general, we're thinking about a hypergraph where we can have an arbitrary number of these elements related by a relation. Okay, so that's kind of the raw material. Now the question is, well, what happens if we use that kind of raw material? Let's say we have, let me find a good example here. Okay, so that might be one of those, a bunch of relations between a bunch of elements. We can represent that as a graph like this. And now we can say, well, what happens if a little bit cellular automaton style, except remember now, we don't have any notion of space or time even here. We just have a notion, we just have these relations between elements. Okay, so let's say we have a little rule that says if we have a set of elements that are related in this way, we'll transform it like that. Okay, so we can represent this rule in this kind of way. Okay, let's just try running that rule. Let's say we started off from something like this and try running it for a few steps. That's what it does. So the same kind of thing that we saw in Rule 30. Very simple rule, very complex behavior. That's what you get after I don't know, just 10, 20 steps. So if you go out and look in this kind of computational universe of possible programs, you see all kinds of things happening. I don't know, here's a collection of things that you get. There's more. So the idea is that even though we started just with this abstract collection of relations between elements, this hypergraph, we have this rewriting rule for hypergraphs, we apply it a bunch of times, we get this very, very big hypergraph. Maybe that big hypergraph is something like space as we know it. And so the sort of foundational idea of what we're doing is to say, let's start with this abstract thing and let's see whether that corresponds to something like space as we know it. Well, let's consider this rule here, for example. Another one of these pretty simple rules. Let's run it for a while. That's what it does. Keep running it. this is the kind of thing it does. It knits basically this thing that looks very much like a two-dimensional grid. Well, we can look at other rules. Here's another one. Oh, here's a rule. Keep running that for a while. It'll create this thing that when we render it like this, it looks like a two-dimensional surface that's curved. Okay, well, so how do we know? Let's say we've grown this very big hypergraph. Let's say it's a 10 to the 400 node hypergraph, as might be the size of the one for our particular universe at this point. What can we say about that hypergraph? Well, given a graph, we can always draw it in lots of different ways, but we can try and characterize how this graph works. For example, we might say, what's the effective dimension of the continuum space that is the limit, the large scale limit of this hypergraph? So a way we can kind of probe that is to say, well, let's imagine we have a graph. We start at some point in the graph. We just start going progressively outward in the graph, and we go, so let's say R steps outward from a given point. We make kind of a ball, a geodesic ball in this graph. How many nodes are there in that geodesic ball? Well, if we have something which is kind of like a two-dimensional grid, the number of nodes is of order R squared. We do the same thing in here, it's of order R cubed. In general, for a d-dimensional, a thing that's going to behave as if it's d-dimensional, we can think that the volume of this geodesic ball grows like R to the d. And indeed, we can measure it for something like this, and we find out, yes, this particular thing is about 2.6 dimensional. And so that gives us a sense in which this hypergraph, when it gets big enough, behaves something like continuum space of some number of dimensions. Now, we can also start asking, what about curvature? We know that if we just measure the area of a circle, it's pi r squared, except on a sphere, there's a correction term that's proportional to the curvature of the sphere. We can look at this, for example, we'll find out that this particular thing indeed is roughly two-dimensional, but has a curvature, and the curvature is actually characterized by the Ricci scalar for the object that we're looking at. Now, it's a big adventure because what we need to do is generalize ideas of differential geometry out of integer dimensional space. That's not something, calculus was kind of built to deal with integer numbers of parameters. We don't really know how to do it for non-integer dimensions, although these models are giving us sort of underpinnings of how that mathematics might work. But in any case, we can then look at what happens in when we look at kind of the large scale structure of these hypergraphs that get built. Are they like kind of flat space of d dimensions? Are they like curved space? How do they work? Well, so now that leads one to the question of, okay, so how does this relate to things like general relativity? Okay, well, to talk about that, I really have to start talking about not just about space, but also about time. And one of the big lessons of 20th century physics is this idea that space and time are somehow closely related relativistically. How does that work in this kind of model? What's one fundamental feature of this model is that there's space, which is represented by kind of the extent of this hypergraph, and there's time, which is sort of a different kind of thing. Time is something that is just the inexorable progress of sort of the computational rewriting of the system. Time means something because of computational irreducibility. Time is the progression of things, and it is an inexorable progression that you can't, that is sort of an irreducible computation going on. By the way, that phenomenon of computational irreducibility finally gives us a way, I think, to clearly understand how things like the second law of thermodynamics work. The second law of thermodynamics is, in a sense, encrypting its initial conditions to the point where no reasonable sort of computationally bounded, coarse-grained observer can decode what happened in the evolution. But that's another sort of sign of kind of the progress of time. But okay, so in our models, space and time seem very different. How then do you get things like Lorentz invariance? Well, the answer is it's a little bit subtle, but let's try and go through it. So the basic point, let me see if I've got a good example of this. Yeah, this is okay. The basic point is to think about what is it that we really notice in the progress of the system. So if we are observers who are ourselves embedded within the system, what is it that we can actually pay attention to? And what we realize is the only thing we really pay attention to is the update events in the system. Because in a sense, you know, imagine there's just one place in the universe that's being updated at any given moment. Well, we won't know that, you know, that might seem like a crazy thing, that there's just this little sort of Turing machine head that's running around the universe updating things. You might say that's obviously wrong because we can plainly see that things are all getting sort of updated together. But the point is, we don't know that any other part of the universe has been updated until that Turing machine head gets inside us and updates us. So when you sort of pull that all back, what you realize is the only thing that observes is these events and the causal relationships between events. So an event, in the case of a hypergraph rewriting system, the event is a particular set of elements, nodes in the hypergraph, are ingested by some hypergraph rewriting rule and turned into something different. This is a case where we just have a string rewriting system where it's just saying every time you see a BA, rewrite it as AB. And this is now showing these yellow things are just the events that take place in this system. Okay, so one feature of these events is that they have a partial order. These events have the property that in order for, let's say, this event here to be able to take place, this event here has to have already happened, because this event here is going to use as part of its input something that was output from this event here. So that means that there's a kind of causal graph that you can draw that represents the causal relationships between those events. That defines a partially ordered set of events. And okay, the next big fact. There is a class of systems in which okay, so I should also have explained that one of the things that's true about the systems we're looking at is they say there is a rewrite rule, sort of try and straighten that out, and we say what do those set of events look like to us if we kind of straighten them out? Well, what they look like is this, and this looks very much like what you might see in an elementary relativity textbook. It's the same kind of idea. The thing you get is exactly Lorentz transformation. And in fact, you can apply that even to a system like this. This is the result of looking at a string rewrite system in a boosted inertial frame. And what you realize is if you compare, okay, so that's kind of the at-rest sort of number of steps it takes to get to the result in the string rewrite system. That's what it takes in a boosted frame. What you're seeing here is essentially time dilation. And in fact, the formulae that show up here are exactly the ones you expect from special relativity. So there's a little bit more there's considerably more to say about this to make this a more formal result. But basically, that's a sort of typical causal graph that you get in an actual system based on hypergraphs. And you can do all the same kinds of things there. And you can show that when there's causal invariance, you can expect that in the large scale limit, you will get special relativity. Well, you can go beyond that, actually. You can say, well, what can we say about, just as we might say we start off from a bunch of discrete molecules in water, and we try and figure out what are the continuum equations that govern that on a large scale, let's say the Navier-Stokes equations in that case. What's the analogous result for our hypergraph systems? What's the large scale equation that governs the behavior of these hypergraph systems? Well, computational irreducibility implies a certain kinds of weak ergodicity assumptions that allow us to sort of use statistical methods. If we assume that, we assume causal invariance, and we assume one more fact. And the one more fact is that the universe is in effect a finite dimensional, not infinite dimensional object on a large spatial scale. If we assume those three facts, we can then derive Einstein's equations. So what that means is that the large scale behavior of these things that we get from these causal graphs and so on corresponds exactly to Einstein's equations. That means that I mentioned that the Ricci scalar is the thing that shows up when you're looking at these growth rates of geodesic balls. That's sort of the beginning of the story that gets you to Einstein's equations from these kinds of systems. Well, the first thing you do is to think about vacuum Einstein's equations. Now, one thing I'm sort of mentioning here is, what is the universe? The universe is just a giant hypergraph. But you say, well, what about all the stuff in the universe, like the protons and the electrons and the quarks and so on? Well, what has to happen is those have to arise as features of this spatial hypergraph in much the same way as those structures arise in something like the cellular automaton, that the underlying system is just following these rules, but they're essentially a topological obstructions that exist in the overall structure of the system that correspond to things like particles. So a question would be, given that if we want to derive the full Einstein's equations, which involve both the vacuum piece and a piece that's involving energy momentum, how can we think about that? I kind of thought we would have to really understand how particles work, but it turns out we don't. It turns out we can have a bulk notion of energy momentum in these systems. And roughly the way it works is that energy is roughly a sign of activity in the network. So slightly more formally, what you find out, activity in the network is basically the presence of events in the causal graph. And so what turns out to be the case is that in our models, energy is essentially the flux of causal edges through space-like hypersurfaces. So in fact, the fact that energy momentum transform relativistically in the same way that space-time does is something that you then can derive in our models. And by the way, you can also derive nice things like E equals mc squared, which is a good crowd-pleasing fact, at least, from our models. And so the thing that that you can get then is energy is a flux of causal edges through space-like hypersurfaces. Momentum is flux through time-like hypersurfaces, and so on. And when you set it up that way, you discover that you indeed get exactly the full form of Einstein's equations, involving the dependence of curvature in space on the presence of energy momentum. So what are the consequences of Einstein's equations? Well, I mean, there are all kinds of consequences, like the present. This is an event horizon and a causal graph. You see those kinds of things. You see some somewhat more exotic kinds of structures than you can see in ordinary general relativity, because we have a theory in which dimension can change as well as curvature in space. There's lots of stuff to say about that and about implications of that for cosmology, for the possibility that the universe started infinite dimensional and sort of gradually cooled down to be three-dimensional and so on, and lots of things that one might be able to see of relics for that in the current universe. But the thing. Let's see, where was I going with this? I was going to, yeah, so another big consequence of general relativity, a sort of a key idea in general relativity, is this notion that the presence of energy momentum produces curvature in space, which essentially turns geodesics. So if you set up a geodesic, I don't know, there's a friendly geodesic. If you set up a geodesic in this hypergraph, you can essentially say that the presence of energy momentum associated with these, and I'm skipping quite many layers of technical detail here, but basically the presence of energy momentum is what leads to the deflection of geodesics in this graph. And that's something that you can essentially prove just as a matter, assuming computational reducibility, causal invariance, et cetera, you can prove that just from the structure of the model. Okay, so what that means is the gravity, the deflection of geodesics by the presence of energy momentum, is something that is a consequence of these models. It comes out in the same way that general relativity comes out. Okay, so let's hold that thought for a minute, because it's going to come back when we talk about quantum mechanics. Okay, so how does quantum mechanics work in a model like this? Well, quantum mechanics is a very important feature in this model, is that quantum mechanics is not just something that you can get in the model, it's something that has to be there. There is no way to escape the fact that there has to be quantum mechanics. So in this sort of big diagram of how the model works, this is kind of going down the left, there's kind of the spatial story. There's the underlying rule, it updates this hypergraph, you get this big spatial hypergraph. But important point about this rule, there are many possible places where these rules could be applied in a given spatial hypergraph. And the question is, which of these updates do you do? Do you have some scheme that just says, do this update and then this one, whatever? Okay, so the point is that the model doesn't define what the sequence is. And that's very much like the difference between like classical physics and quantum physics. In classical physics, you throw a ball, it follows a definite trajectory. In quantum physics, you have the idea, you throw a ball, there are many possible trajectories that get probed, and you get to know what the probabilities of different outcomes are. Well, in these models, what we look at are we just think about all those possible paths, all this so-called what we call a multi-way graph that that follows all these possible updates that you could do. And so if we look at one of these multi-way graphs, we can look at one. Let's find one here. Here's a multi-way graph just for a string rewriting system. This is not for hypergraphs, just for strings. And what we see is it branches. There are two possible things that can happen here. Sometimes it merges as well. Well, and so this is representing, each one of these blue squares is representing, let's say, the state of the universe, a particular quantum state of the universe. And what we're seeing is there can be multiple outcomes from one of these states, or things can merge together. And by the way, that merging is important because it turns out the causal invariance implies that there's an equal amount of branching and merging. It implies that every time there's a branch, there will eventually be a merge. It may take a while, but there will eventually be a merge. That's the consequence of causal invariance for the multi-way graph. Okay, so what happens then is we're thinking about this as each one of those possible states is essentially a possible quantum state. And so what we're seeing here is this whole kind of network of how different quantum states evolve into each other and so on. And let me not particularly go down the story of how quantum measurement works. Essentially what happens is that a quantum observer is operating just as we have to sort of foliate space-time in order to make sense of what's happening in the universe. So similarly, a quantum observer is effectively foliating this multi-way graph to decide what counts as to determine the measurements that they're doing. And there are lots of different ways you can foliate this multi-way graph. I might mention, I think there's a Dutch interest in the ontological basis approach to these kinds of things, and there's a very nice way of getting that and kind of Bohmian mechanics out of this by looking at a particular way of doing that kind of foliation and so on. But the thing well, one important thing to say, let me not get too much into quantum measurement here. I'll be happy to talk about it, but it's a slightly different story. But basically, quantum measurement is a story very much like the story of picking frames in relativity. And what we're seeing here is but perhaps the more interesting thing to look at is if we look at this this multi-way graph and we look at its foliations, we can say, let's make a map at a particular slice in this foliation, essentially at a particular time. Let's make a map that shows how these different quantum states are related to each other. What common ancestry do these quantum states have? In effect, what entanglement do these quantum states have? And this is what we call a branchial graph. It's a graph that is representing just as in space-time, we're looking at a causal graph, we're foliating it, we're saying the slices across that causal graph represent physical space. So the foliations of this multi-way graph represent another kind of space that we call branchial space, the space of quantum branches, where we can represent entanglements between those quantum branches by these kinds of graphs. And that's another kind of space, this branchial space. That is not the same as physical space. It's a different kind of thing. Okay, so the next thing we can ask is, what is the continuum limit of this multi-way graph? What can we say about that continuum limit? In the ordinary spatial hypergraph, what we're saying is continuum limit is like a manifold that's like, might be like space or something. In this case, the continuum limit seems more like a Hilbert space of some kind. We don't know mathematically exactly how it's structured, but what we can do is we can ask questions about things like, what are geodesics like in this multi-way graph? And it turns out that just as the same notion of energy that we can set up in space-time is also a notion of energy in this kind of multi-way graph, in this quantum multi-way graph. There's an analog, there's a multi-way causal graph, which is the multi-way analog of the ordinary causal graph, and we can make the same definition of energy for that as we did in the standard causal graph. And when we do that, we find a very interesting fact. We find that the paths of geodesics in branchial space are deflected by the presence of energy. So what does this mean? Well, we have to be a little bit more careful, and actually what is of interest is not the flux of causal edges through space-like hypersurfaces, more divergence of causal edges, which turns out to be the Lagrangian density. You can interpret that as the Lagrangian density, quantum Lagrangian density. And so what we're finding is that these JD6 in branchial space are being deflected by the presence of Lagrangian density. Well, that might remind you of something. In the Feynman path integral, what one's looking at is that it's e to the I s over h bar, where s is the integral of the Lagrangian density. So what we're seeing is that what's happening in branchial, just as in physical space, the presence of energy momentum is deflecting JD6, the same exact thing is happening in branchial space. The presence of energy momentum is deflecting these JD6 in branchial space. Okay, so what? Well, the point is that these JD6 are effectively carrying, when you think about what is the amplitude, what is the probability for something to happen, but it starts off with amplitudes. What happens when basically what's happening is you want to assign a weight to each of these states. And in quantum mechanics, one of the things that's been done is to assume that what we're dealing with is always a quantum amplitude, which is a single complex number. I think in reality, it's much better to think of it as a magnitude separate from a phase. By the way, I consider that one of two mistakes made in 20th century physics. The first mistake was assuming that space and time are the same kind of thing, which I don't think is true intrinsically. And the second is assuming that magnitude and phase of a quantum amplitude are sort of come from the same place. In our models, again, much more detail can be given, but the magnitude comes from essentially path counting in the multi-way graph. And the phase turns out to be essentially the position in branchial space. So essentially what's happening is when you see two-slit experiment or something, what's happening is that the thing you don't see is being routed off to a corner of branchial space that you do not see. And that's what happens. That's how the phase is derived in the quantum amplitude. But the thing that I think is like quite spectacular is this fact that essentially you might say, what's the relationship between gravity, Einstein's equations, and quantum mechanics and the path integral and so on? The answer is they're the same thing in these models. The Einstein equations are all about deflection of JD6 in physical space. The path integral is about the deflection of JD6 in branchial space. So you can start to see, when you're looking at things like black holes and so on, you can see the interplay between physical space and branchial space, and you can start talking about how information gets handled at black holes and how holographic principles come in from the correspondence between branchial space and physical space, which are essentially different projections of the multi-way causal graph, et cetera, et cetera, et cetera. So sort of the big picture here, I don't want to go on too much longer here because is that from this very underlying, very simple computational ideas, one is able to derive lots of things which we know from 20th century physics. And by the way, I can go on and talk about all kinds of particular things in quantum mechanics and general relativity and so on that we've been able to derive. I think one of the things that we've been really trying to do is what I might call proof by compilation. So in other words, do we really reproduce general relativity? Well, our model actually provides a way of doing numerical relativity. So we can actually, we haven't done it yet, we can actually compute a black hole merger in our model. Now, we think mathematically that our model should limit to ordinary general relativity. We subject to certain assumptions, we have a proof of that. But we can also actually operationally see that the model reproduces the same thing that we get from the discretization of the Einstein equations, for example. And similarly, in the case of in the quantum area, one thing we have done is a proof by compilation for quantum computing. We've taken a quantum computing framework in Wolfram language, and we literally have a compiler that goes from that quantum computing framework to multi-way graphs. And in fact, more formally, and Jonathan's been a key person in this, we've been able to connect our model to categorical quantum mechanics and show that you can essentially compile ZX calculus of categorical quantum mechanics into our multi-way graphs. It's actually even a computationally efficient thing to think about things that way. So that's kind of, and there are a lot of other details about how we think about lots of different things in physics, spin statistics, all kinds of things, but much that we haven't figured out, some that we have figured out. But in any case, that's sort of the big picture there. But let me sort of zoom out a little bit, and let me just say a few more things, and then I'd like to wrap up what I have to say at least. Let me talk a little bit about the sort of more philosophical level of what's going on in a model like this. Then I'll talk a little bit about its implications in areas like mathematics. So, okay. So one of the things that is perhaps is interesting here. Well, okay. First thing is one of the big surprises to me about what's happened with this model is how easy it's been. That is, I had thought that we might be able to find some model that might plausibly reproduce the first 10 to the minus 100 seconds of the universe, but then we would get completely stuck in a morass of computational irreducibility. We wouldn't be able to get any further. But so the big surprise is that we can actually say things on the basis of this model. Well, in a sense, what's happening is that there's sort of a bedrock of computational irreducibility. The details of what's happening in that spatial hypergraph, lots of computational irreducibility. But one feature of computational irreducibility is whenever there is always pockets of reducibility to be found. And what's essentially happened is 20th century physics is about two big pockets of computational reducibility, relativity and quantum mechanics. And in a sense, the fact that we humans don't think that the universe is an infinitely complicated place. We can tell that there are actual predictions we can make about what's going to happen, means there's some computational reducibility to the universe, which 20th century physics is kind of concentrated in these two big theories. And essentially what we've discovered is that on top of this kind of layer of computational irreducibility, which happens in these models, there are a couple of slices of computational reducibility that we are able to tap into and that allow us to make a connection with both what we observe in the world and with 20th century physics. Okay, so one of the mysteries of working on something like this is, okay, let's say we actually get something which is a particular rule, and from that particular rule, we can really reproduce 3 dimensions of space, the electron-muon mass ratio, all these kinds of things. And we can hold it up and we say, this is the rule for our universe. We've successfully reduced physics to mathematics, basically. Okay, so that's a very strange moment because in a sense, a lot of the history of science for the last close to 500 years has been a story of why we're not special. You know, Copernicus on, it's been a story of, oh no, we're not really that special. We're just this random planet around a random star, random galaxy, et cetera, et cetera, et cetera. So how come we're the winners who get this simple rule for our universe? Why isn't the rule for our universe some unbelievably complicated thing, a randomly chosen rule, randomly chosen from a set of all possible rules? Okay, so I didn't think we were going to have any scientific answer to that question, but turns out we do. So here's how it works. So I mentioned that one of the features of our models is that at every step, essentially, the rule one's using can be applied in many different ways. And that leads to this multi-way graph, and that leads to quantum mechanics. Okay, so you can go much more extreme than that. You can say, not only will we apply every particular rule, the particular rule we have in all possible ways, let's also just apply all possible rules. And from that, we have this giant rulial multi-way graph that represents the doing of all possible rules. Okay, you might say, how can you possibly say anything about that? Well, it turns out that that system inevitably has causal invariance. And that means that there are things that can be reliably said, even independent of sort of how complicated it is. We can slice it in particular ways and we'll always somehow get a consistent answer. And in a sense, so then what are the reference frames of rulial space? The reference frames of rulial space are essentially description languages for the universe. And so essentially what we're saying is, in a particular reference frame, we will attribute the behavior of the universe to some particular underlying rule. That's in our particular rulial reference frame. With our particular sensory apparatus and so on, we say there's a notion of space, there's a notion of time, et cetera, et cetera, et cetera. That implies a certain rulial reference frame and implies a certain description language and implies that we are attributing the behavior of the universe to a particular rule. But we could imagine a different rulial reference frame, a completely different description language for the world. And now it's you know, I always used to say when we think about, you know, extraterrestrial intelligence, which I think is kind of a strange concept in the world of computational equivalence, but that's a different issue. But we say, well, at least the aliens will have the same physics as us. But I don't think that's true, because the fact that we have a particular rulal reference frame that's determined by our particular way of existing, it's not necessarily shared. We can have utterly incoherent views of the universe. I mean, even imagine if we were much bigger than we are, we would have a very different view of, the effect of the speed of light and so on. By the way, I might mention that in our models, there's a second kind of scale that exists in addition to speed of light. The second scale that exists is a maximum entanglement speed, which is essentially talking about extent in branchial space. And that maximum entanglement speed, for example, in the merger of large black holes, it may be that the maximum entanglement speed is actually a limiting factor in addition to the speed of light, and that can lead to measurable consequences and so on. But in any case, the thing that the basic point is we can have these utterly incoherent descriptions of the universe that still are talking about the same underlying universe. And that leads us to realize that it's this strange thing that we have picked particular physics, like 20th century physics, locked onto these particular things which are relevant to us because of the way our senses work and so on. But we could have chosen probably quite different things. And it's sort of a humility-inducing thing in a different way than kind of the Copernican humility, because in a sense, what we're saying is we just have a particular description language. There are lots of others. For myself, as having spent my life as a computational language designer, this is kind of an interesting thing to realize that what we're doing here in making a model for physics, what we're really doing, it's like a language design problem. What it's doing is it's saying, can we invent a language for describing what's going on in our universe that correctly interpolates between us as humans and what we can understand, the universe in its operation, and now also the kind of intermediate level of computation. Well, okay, so this is one of the things that we're realizing here is you can have these sort of utterly incoherent views of physics. What knits all of these together? There's actually something we already know, which is as soon as we have almost any of these systems, we will have something which operates as a universal computer. And in a sense, what we're saying is, once we say the universe is computational, like a Turing machine, not like a hypercomputer, just like a Turing machine, then in a sense, it can emulate any other Turing machine and any other universe. So in a sense, that's how you derive this causal invariance of rulal multi-way systems and so on, is by knowing that in principle you can translate the computation that's represented by one model to the computation that's represented by another model. And that's kind of the underlying story, is that the final thing we know that is not sort of movable is the principle of computational equivalence. That's the thing that allows us to then build up this whole sort of structure that lets us get to these kinds of ideas about how to make a fundamental model of physics. So I just mention a couple of other things. So one question is, from a sort of the point of view of mathematics, what is that rulal multi-way system? What is that limiting structure? Actually, we can look at that. Let me try and pull up something here to show you that. Here we go. So we can, if I get this to come up, see if this works. We can look at a simpler case of rulal space. Let's look at rulal space for Turing machines. Okay, so there's a little friendly Turing machine doing its thing, and now let's look at, and this is a non-deterministic Turing machine that can have several different things happen. But now let's look at rulal Turing machine space. That's a space where basically all possible Turing machine rules, it's kind of the maximally non-deterministic Turing machine. All possible Turing machine rules happen. And so now we can construct that rulal multi-way space for Turing machines. And we can start making, there's all sorts of interesting mathematics about this, which I've figured out some parts of. It's kind of interesting to see the connection with the computational complexity theory, because what we're seeing there, the full picture is all possible non-deterministic Turing machine computations. The red piece is deterministic ones. Any particular deterministic Turing machine computation is a particular path in the rulal multi-way graph. There's a particular deterministic Turing machine. So in a sense, the P versus NP problem is a question that can be stated in terms of the rulal multi-way graph of Turing machines, and it becomes sort of a geometrical question about this. And so there's sort of a geometrization of computational complexity theory that one can imagine. But from a mathematical point of view, we can ask, what does this mean? What is the limit of this rulal graph? And it turns out there's a way to think about this, and it uses category theory. And so the idea is we start off thinking about our original hypergraph. Our original hypergraph is like a weak version of a category, and of an ordinary one category. We're just making, morphisms, connecting objects, et cetera, et cetera, et cetera. Okay, so then when we get to the causal graph, we're essentially making, that's like making two categories. We're making transformations between elements in the original graph. And we can keep going, and we can eventually get to an infinity category. And the infinity category is essentially this rulal graph. And so it turns out that these rulal graphs, rulal multi-way systems, are closely related to things like the infinity groupoid of Grothendieck, and all kinds of mathematical ideas related to that turn out to show up in this. And we can start then using hypotheses that exist about infinity groupoids to then go backwards and understand more about what can be true about physics from that. And just to mention one more thing, and then I'll wrap up, about how this relates to mathematics. So one of the things, let me pull up something here. What's a good place to go? When we make these multi-way graphs, we've kind of seen something like this before, and we've seen it before in mathematics. And let me show you an example. When we make a proof in mathematics, what we are typically doing, here's a little proof. This is saying, here are some axioms. Now what we want to do to make a proof is we want to find a path that uses these axioms and gets from one thing to another. So essentially a proof, we can look at the space of all possible results in mathematics is a multi-way graph that comes by just using the axioms of mathematics as the moves in this multi-way graph. And then the true theorems in mathematics correspond to paths in this multi-way graph. And so then we can start asking, how does that relate to what we know about, what we know, for example, about physics? So one thing I looked at recently, let me pull this up. Sorry, I wasn't properly prepared here, but let me, so one question is, let's look at, we have this kind of multi-way graph of all possible things that happen in mathematics. What are the things that actually historically happen in mathematics? So I looked at Euclid, and you can just look at, this loads in, that is the, that there is actually the graph that represents the relationship between theorems in Euclid's elements. And in a sense, what this is a piece of empirical metamathematics. There's a set of all possible connections between theorems that exists that are derivable from the axioms of geometry. These are the particular ones that Euclid chose to pick out, and one can make a whole analysis of this. But one of the things that's interesting is to try to understand the space of metamathematics, just as we're understanding physical space. And essentially, metamathematics is a story of multi-way graphs, and you can think of the limit, the infinite limit of mathematics. You think of mathematics as it's actually been done. It's about 3 million theorems have been published in the history of mathematics. You can ask, what's the infinite limit of mathematics when you have an infinite number of theorems? What does this space of what does this mathematical space look like? What's its curvature? What happens to geodesics in metamathematical space? Those are shortest proofs. What happens to event horizons in metamathematical space? All these kinds of things. And so what you can start thinking about is applying essentially physics ideas to metamathematics, ideas from metamathematics, ideas from proof theory to physics. And that's a very interesting interplay of things. And what we see is a model. So one of the big mysteries of mathematics is, why can it be done at all? The reason mathematics is hard is because of computational irreducibility. We know the underlying axioms, but to work out what theorems are true can involve irreducible amounts of essentially computational work. But the surprise is that mathematics is possible. That is, that it isn't the case that the typical theorem you try to prove is undecidable, that the typical path that you have to follow to get from sort of left-hand side to right-hand side is infinitely long. And that's always been very mysterious to me, because when I look in the computational universe and I look at, J-random cellular automaton, the typical thing that I might try to prove about it tends to be undecidable. but yet in mathematics, as we humans have practiced it, we're successfully able to prove theorems without falling into undecidability. And that turns out to be a consequence. We can start to understand in terms of sort of this metamathematical space, we can start to understand how the geography of metamathematical space is set up, and how we humans populate different parts of metamathematical space. And essentially we're building sort of building out pieces of metamathematical space, exploring those pieces rather than being sort of plopped into the middle of metamathematical space where you end up with undecidability. But so in any case, the thing that I think is interesting is this interplay between ideas of proofs, ideas of geodesics in physical space, the idea of multi-way graphs, the use of, there are very practical consequences about thinking about causal graphs and thinking about speeding up automated theorem proving by looking at high energy parts of the metamathematical causal graph, things like this. So that's an interesting interplay. I'll just mention one more interplay, which is with distributed computing. So one of the things that that happens in a sense, the universe in our models is the biggest distributed computer. And one feature of distributed computing is always this question of when you're doing distributed computing, you have many different things that are happening, but you don't necessarily know which happened first. You know some partial order of what has to happen, what is the causal relationships between the things that have to happen, but you don't necessarily know what happens first. And it's hard to program in that kind of distributed environment. What we're realizing is that that is exactly the same story as the story of causal graphs, relativity, and so on in the physics case. And so what we're realizing is that we can make this kind of dictionary between ideas from distributed computing. Eventual consistency of distributed databases is causal invariance, for example. Race conditions are branch pairs in the multi-way graph. These are correspondences between distributed computing and physics, basically. And why is that important? It's important because there are ideas from distributed computing that we can now import into physics, but perhaps even more importantly, there are ideas from physics, which is a very well-developed area, that we can now export or import into distributed computing. And so it will happen that people will end up starting to talk about, I am programming this distributed computing system in a certain reference frame. That will be a kind of concept that it allows one to use the ideas of 20th century physics to kind of organize how one's thinking about things computationally. And it turns out that there's this whole framework that we've built with these very simple systems that come from just looking at rewrites of relations between elements in hypergraphs and so on. It's a very rich kind of source of models for things, and we've even been looking at making models where one particular area is making distributed blockchains using this. That's an interesting technological application. There are also potential implications to modeling biological evolution and a variety of other things. In a sense, what's happening is cellular automata are a good generic model of a sort of distributed space-time parallel kind of thing. These models are a good model of something where there is no synchronicity, there's no notion of space that's already been laid out. It's just sort of a much rawer form of computation. I could go on and talk about, I've been actually rather obsessed recently with the studying that there are a lot of connections to other kinds of foundational ideas about computation that seem to be both illuminated by these approaches and seem to illuminate these approaches. But anyway, I should probably stop there. And let me just sort of summarize that the kind of glib summary would be, it really does seem to be computation all the way down, so to speak. It really seems that this computational paradigm is providing us a way to understand in great detail how fundamental physics works, the kind of machine code of the universe. A thing to also mention is that a lot of approaches to mathematical physics, particularly ones over the last few decades, whether it's causal set theory or topos theory or I don't know, spin networks or mentioned categorical quantum mechanics, a lot of different approaches. A lot of these approaches seem to attach to our models. It seems like our models provide a concrete grounding for these kinds of approaches. So for example, in the case of causal set theory, what has become clear, this is work by Jonathan recently, is that its causal set theory is just sort of assuming a certain degree of randomness, and then producing causal graphs just like our causal graphs, except that we have a way to generate the causal graphs. We don't just say, throw down a Poisson distribution. We say, this is how the causal graph is generated. But it so happens, but if you just assume it's random in that way, you get causal set theory. And this is this kind of correspondence between these models and these things that have been developed in mathematical physics, I think is very fertile. I kind of view it historically a little bit like what happened in 1936-ish when things like Turing machines were invented, because basically what had happened was there had been pre-existing ideas about computation. One that's almost exactly 100 years old was combinators, another lambda calculus, another general recursive functions, post-tag systems, all these kinds of things. These were all essentially models of grounding. It wasn't clear how they all connected together. Turing machines was sort of a more concrete way of thinking about this process of computation, and that allowed this to be that area to be more systematically developed. And I kind of feel like what we're managing to do here is we've ended up with this very minimal model that is essentially a concrete grounding that can read on many of these kinds of approaches to mathematical physics. And I think that's a really fertile thing and something that is of great benefit, both in terms of making further progress on our models and on making further progress in these directions of mathematical physics. But I think the main sort of message is, in a sense, what do we learn from knowing something about how fundamental physics works? It's kind of like the Copernicus story. I mean, the fact that one had pretty good ways to do astronomical with epicycles, it was not a big innovation to compute things in a different way. But what was more important was the conceptual framework that changed about what one could expect to do based on sort of, in that particular case, one's sort of everyday senses versus from science. And I think here the main thing that we realize is we already knew computation was an important thing. But if it's really sort of computation all the way down, that means that we really have to think computationally about everything. And I think that that means that concepts like computational reducibility, we kind of know that they have to be important for things. And we kind of realize that, just as things like energy, momentum, and so on were ideas that came out of sort of the mathematics of mechanics, so things like computational reducibility and energy momentum get sort of applied in areas for thinking about things very different from mechanics. Computational reducibility actually is more directly applicable, but is something that we can expect to see applied all over the place. All right, I should stop there, and I'm happy to. I'm looking forward to this discussion. It seemed like a very interesting panel, so I really am. I'm looking forward to discussion here. But thank you very much.
Okay, well, thank you very much, Steve, for this wonderful introduction, wonderful expose on all these radically new ideas to talk about things that we thought we were very familiar with, but your perspective is kind of shaky. And so I would say you have taken us beyond the horizon, at least for many of us, and it's extremely stimulating. So I'm very happy to hear that you are still in for some discussion with our
Please.
Panel. And so let me introduce the members of our panel, and I will do it just in order. The first is Sonja Smets. She is a professor of philosophy and logic, in particular epistemology. Maybe you well, Sonja is there. Yeah.
Hello.
Our second member is Professor Klaas Landsman. He's a professor of mathematical physics of the University of Nijmegen, and he's spending lots of time on foundations in physics in a very broad sense. The third member is Professor Max Welling. He's a professor of information science, in particular machine learning. And finally, Jan de Boer, who is a professor of theoretical physics and is a great expert on string theory, so the other fundamental theory of physics. So I think we have a rather diverse group here. And
this is great. I want to have this conversation. Let's start.
Okay, so
who wants to launch in here?
Well, let's do it this way. Maybe to begin, I would like to kind of give the people a word, because we are in a multi-local situation here, a COVID-proof way of doing this. So I would like to invite them maybe in turn a little bit, and then we can see how the discussion develops. But certainly we welcome your reactions, of course, to what the comments and questions are that the people will ask. So let me start with Sonja. Maybe I can ask you to give some comments or questions, please.
Okay, yes. Well, thanks for a very nice presentation. I like to talk about the idea of this unified theory for a computational model of the universe, because many had this idea of a unified theory of everything, and they didn't succeed till now. So why do you think this project is going to succeed? And specifically, because even if on the ontologically level, you can explain certain aspects, you can explain the ZX calculus of quantum theory and parts of relativity, but why would we epistemologically, in our way of thinking, be able to explain it or comprehend it even? We might even, if I understand your lecture, understand just slices of it. I can understand one slice and the other slice. It doesn't mean I can have unified theory that explains both sides together.
Right. Okay. So you know, I didn't know this was going to work. In fact, I didn't think it was going to work. So the fact that things have gone as well as they have is a big surprise to me. You know, when you try and assess scientific theories, for me, one of the big questions is how much do you put in for how much do you get out? That is, if you have a theory and you're trying to explain some phenomena, and every time you find a new phenomenon, you have to say, oh, let's add a little patch to the theory to cover that phenomenon. That's a very bad sign for the theory. What's been really surprising about what we've been doing is this one very minimal theory. We keep on being able to explain more and more and more stuff. And so far, we haven't hit a wall. So far, there's been nothing that is known from existing physics where we say we just don't know how that can possibly say. That may be technically complicated to understand, but it's not like, oh, you just can't get there from here. Now the question is, let's say, you know, this is a sort of general problem of scientific induction. You know, let's say we have successfully explained 100 phenomena, 100 core phenomena about the world. Does that mean we've nailed it? Does that mean we've actually got the rule for the universe or not? Now, ultimately, we don't know, because ultimately it could be that if we assume the universe is simple, then yes, we could say, you know, we look at all possible simple rules, we could say, if the universe is that simple, there's no other rule that can explain those phenomena. Therefore, if the rule is of this type, we've nailed it. We've got the whole theory for the universe. But we don't know for sure. We don't know that there isn't, you know, mostly this very simple rule, but there's a miracle that happens somewhere on the side of the universe that we'll never know about, and that you know does not follow this rule. We'll never know that. That's just the nature of you know, how things work, sort of in the philosophy of science. But the fact is that the thing that I think is and perhaps it's a, you know, an aesthetic belief, perhaps I should say, is that if we succeed in finding enough stuff that is precisely nails the way our universe works, then it's a pretty good inference that we've really got it. We don't know for sure. We'll never know for sure. I think that you know, if you really want to kind of you know, the philosophical things that I'm not sure I've totally wrapped my brain fully around is this whole business about rulal multi-way space, and the fact that different ways of thinking about the universe lead to different rules, but the whole thing is still part of the same fundamental model. I don't think I fully understood that, and that is a and you can go even further than that. And I think the remaining big mystery is, okay, if there is an abstract rule that reproduces our universe, why does the universe exist at all? Can we say something about that? And my current little suspicion is that we might be able to prove a theorem, I don't know how useful the theorem will be, that says, a little bit like Gödel's second incompleteness theorem, that basically says, for entities within our universe, the statement the universe exists is unprovable. So which would be at least philosophically fun. I'm not sure how useful it would be, but it would at least be philosophically fun. But yeah, I mean, you're absolutely right that we will never know. You know, it's the nature of scientific induction. We'll never know for sure we've actually nailed it. But we can be, you know, at an aesthetic level, we can be increasingly certain, I think.
But why would there...
you know, in terms of why, you know, the history of sort of people trying to find fundamental theories of physics, you know, when I was writing kind of a historical background for this project, I went through and kind of reviewed the story of that. It's actually a surprisingly short story. You know, you would think it's the big problem in science. People would have been doing it all the time, but they haven't. You know, in a sense, there was the sort of ancient Greek, you know, the ancient Greeks had a pretty good idea. They said the universe really is going to be made up from something we can understand and maybe many copies of the same thing and so on, but they didn't have the same scientific framework we have. Then, you know, come around to Newton and people like that, people briefly thought, oh, the universe must be all about, you know, the universal law of gravity. Later on, it must be all about fields, electromagnetic fields, other kinds of fields. Then in the, you know, in the age of particle physics, quantum field theory, all about that and so on. And I think what's happened is there have been, I don't know, maybe half a dozen, not much more than that, serious times when people have had paradigms that looked like they actually might have a fundamental theory of physics. I think that, you know, a lot of what we've done could have been done, in principle, could have been done 100 years ago. In fact, if you look, people keep on sending me these quotes from Einstein, where he basically says, I'm pretty sure space-time is going to be discrete, but we do not have the tools right now to be able to explore that idea. So I think, you know, what's happened is we have this paradigm of computation. We have, in perhaps my particular case, I've spent decades doing experiments in the computational universe that give one intuition about how things work. That intuition is fairly necessary to make, you know, a lot of things that we've hypothesized are the result of doing those computational experiments. And that's, I think, a necessary piece of the story, probably. Although you could say, well, you don't really need that. You could just make the hypothesis and then do the mathematics around it. But, you know, so I think I mean, the truth is also in the progress of science, and this is more a statement about the sociology of science than it is about the content of science, you know, the fact, you know, going after something as big as, let's go try and find a fundamental theory of physics based on a different paradigm for thinking about science. That's not your average, get a good grant to do your next piece of academic work type project. And, you know, I've been fortunate enough that the, you know, the trajectory of my particular life has meant that that's not the world that I'm in. And so, you know, for me, it's kind of, you know, it's possible to do these very large projects. I mean, I might say, just by way of sort of personal comment, I mean, the underlying model here that's based on these rewrite rules for hypergraphs and so on, it is something of an embarrassment to me because that model is deeply similar to the fundamental principle that Wolfram language and basically all the computational language stuff that I've done for 40 years works on. It's all about rewrite rules for symbolic expressions. The thing that I missed was when I do rewrite rules for symbolic expressions in computational language, the symbolic expressions have a built-in meaning. It's pluses and timeses and things that actually, but what this is a pure disembodied symbolic structure where the points in space mean nothing, where they're just entities. They don't have a, you know, we don't say that one is called plus, that one is called times. They're just pure sort of, and it's the same thing, by the way, in applying category theory to what we're doing. It's the same using the infrastructure of category theory, but not the meaning that is put into category theory. Anyway, it sounds like you have more to say. Please, I'm sorry, I'm yakking on here.
Okay.
No, well, this is very nice. I think it's logic-based, and it means syntax seems to be the key here. And
well, yes, right. I mean, it could have been, yeah. Lucretius almost had this, so to speak. I mean, Lucretius had this interesting idea that, you know, the world is made up from, you know, the world is made up of atoms by rules similar to the rules by which a language is made up from the you know, through its grammar. Yes, this is a, you know, conceptually, this is a, you know, this comes out of that tradition.
I understand.
Okay. Thank you. I think we should proceed, and let me ask Klaas Landsman. Right. We're talking about foundational issues, so maybe you want to ask something.
Yeah, I'll just ask two unrelated questions. First, thanks for your exceptional talk, which I find splendid. So my first question is about your principle of computational irreducibility, which, for the benefit of the audience, I will just repeat from your own website, Wolfram Math World. So it says, while many computations admit shortcuts that allow them to be performed more rapidly, others cannot be sped up. Computations that cannot be sped up by means of any shortcut are called computationally irreducible. The principle of computational reducibility says that the only way to determine the answer to a computational irreducible question is to perform or simulate the computation. Now, this reminds me of Kolmogorov's definition of randomness, in the sense that the pattern is declared random if it is its own shortest description, or more precisely, that any computer program that generates the pattern is at least as long as the description of the pattern. And so my question is about the relationship between that notion of randomness and your principle of computational reducibility.
Right.
And would you agree that if these are related, that a universe of the kind you describe is fundamentally random?
Okay, so it's a very interesting question. And let me try and unpack it. So there's this idea of kind of Chaitin-Kolmogorov complexity that says, what you're interested in is the sort of the true information content of a thing is the length of the shortest program that generates that thing. And you say that something is random if the length of the shortest program to generate it is comparable in length to the thing itself. So for example, something like pi is definitely not, Chaitin-Kolmogorov random, not algorithmically random, because it has a very simple formula for generating it, and yet its digits, once generated, seem for all practical purposes random. Rule 30 is exactly the same way. Rule 30 makes randomness in a way that does not come from algorithmic randomness. The algorithmic complexity of Rule 30 is absolutely tiny. It's just this tiny little rule. But what you generate is this sequence that for all practical purposes seems random. It's the same story as with pi, that you're generating. So the big question then is my friend Greg Chaitin, who was one of the originators of this algorithmic randomness idea, we've had a long-running discussion, which I think now he's, to my surprise, I think we've been able to answer, which is the universe like pi or like omega? So omega is this constant that Greg defined that is this algorithmically random number that cannot be, for which there's no program shorter than the digits of it itself that generates that number. So the question is the universe random in the sense of omega, or is it random and complex in the sense of pi, in the sense that there's a simple rule, but it seems to us random?
This is essentially my question, yes.
Right. So basically, according to our model of physics, the universe is like pi and not like omega. So, but that has a very important consequence, because what does it mean that the universe seems to us random? It means that with our sensory apparatus, with our means of analysis, there are aspects of the universe that we can't decode. So that becomes a story. I mean, that's basically the fact that, the fact that encryption is possible, the fact that there is a way to encode something so that it is decodable, but it's a reversible thing, but it requires, cryptanalysis is hard. So I'm mixing up several concepts here. So I'm kind of cheating a little bit here because I'm mixing up. Let's just say that the basic point is that I think it's very important. The concept of coarse graining, which exists in statistical mechanics, which is the thing you need in order to be able to derive the second law of thermodynamics, has always been a mysterious thing. For 150 years, people have said, in principle, you can run the movie of all the gas molecules backwards and you can have them all go back into the little bottle. But in practice, that doesn't happen. And we say, because we make only coarse-grained measurements, we never see that happening somehow. Well, now we have a more precise way to talk about that by saying the observer is computationally bounded, and that computational boundedness of the observer has all kinds of consequences for these models and for understanding what count as valid possible reference frames in relativity. It has connections to results in relativity, et cetera, et cetera, et cetera. But the basic answer to your question is, in our models, the universe is not algorithmically random. And in fact, there is no algorithmic randomness in the universe. Quantum mechanics isn't algorithmically random. There isn't any. The universe is a finite computational thing from an algorithmic randomness point of view.
Well, thanks a lot. I had expected the opposite answer, but now thanks for clarifying this. My second and last question has nothing to do with it. Namely, you seem to sort of exhibit a totally new way of doing science. You put all out into the open. I think you can even watch your brainstorms, you put your notebooks out, your entire archives. How did you get there? And would you recommend this to universities as a new model? And why would you do this?
Right. I mean, look, I did it because why not? In the sense that I think, you know, I want to make what we're doing as accessible as possible. You know, for me, why am I doing this project? I'm doing this project because I find it interesting. You know, it's, I figure it is more fun if I can, you know, let more people be as involved as possible in what we're doing. And this is a good way to do it. Now, in terms of live streaming, I started doing that a couple of years ago. I started live streaming our internal software design meetings because I think they're pretty interesting. And I think that they, and I think it's also useful for people who use our language to understand how decisions were made and so on and so on. And it turned out that was really valuable because we get, you know, I do these almost every day. I'll be doing a live stream actually later today about physics project actually, you know, we get real-time feedback and very useful, interesting suggestions from people in real time. It's like kind of crowdsourcing a lot of ideas and so on. I think, you know, my notion is it's why not share it as much as one can with the world. Now, in terms of, that's a very interesting question, which nobody has asked before, is whether universities should do this. It's a really good thing to do. I mean, I think it's a, you know, I think one doesn't get, you know, when we started doing this kind of live streaming software design meetings, people said, there's just nowhere else you can find this kind of thing. There's no other, you know, this is the only source of how these kinds of decisions are made, how you think about these kinds of things. I think similarly for this physics project, I just don't think you can find anywhere you know, the real front line, what's actually happening. I find it interesting, and it's you know, we started doing this and we were having these incredibly technical conversations about mathematical physics, and we had thousands of people watching this. It's like, this is really kind of cool. This is interesting for people. And it's, you know, I think it's a valuable thing in terms of you know, spreading ideas of science and kind of the what's involved in doing science to a broader range of people. So I'm, you know, I think that's really great. You know, it really helps probably that, you know, with the tool set that we've built with our whole computational language and so on, things can happen quite quickly. You know, I can do a computational experiment. This afternoon, I'll probably make a mess of it because I'm going to be working on something on a live stream. But, you know, you can do one of these computational experiments and things are happening. And you can actually, you know, you actually see things go on in fairly real time. It's not kind of like a boring, oh, it's this very much is happening.
Right, so it's largely an outreach effort as opposed to speeding up the development of the program. Or does that play a role?
No, I mean, that's also part of it. I mean, we've you know, we get great suggestions, and also people have gotten involved through, you know, through the fact that we've had all this stuff be opened up. I mean, for example, the fact that the software tools for everything we've done, you know, if you look at the you know, all these papers that we're writing about the physics project, you can, well, at least mine, I don't know about Jonathan's actually, but at least mine, you can click on any picture and you'll get the code that made that picture, and you can just run that yourself. And that's and you know, what's cool is people are doing it, and you know, what would be, you know, where people would often you know, say, oh, it's a huge struggle to be able to reproduce this, I don't know whether I can, you know, I don't even see why it's true, et cetera, et cetera, et cetera. Just click it, copy it, run the code, you know, it does what it does. And I, you know, I think it's look, I've been very keen on this idea of being able to have sort of transporting ideas through computational language. And this is a real instantiation of being able to do that, where you're saying, not only do you say, you can read my paper, here's the formula in the paper, but also here's this piece of computational language and you can run it yourself and you can explore it and play with it.
Yeah, so it's the extreme of open access. It's also reminiscent of von Neumann, who could have made money by selling his computer to IBM, but felt it should be in the public domain because it would develop the technology more rapidly if it were public.
I'm not sure about that story, because when I was at the Institute for Advanced Study in the 80s, they were the last people who'd worked with von Neumann was still there. The story they told was different from that. The story they told was that when the mathematicians at the Institute, actually I was there, a very interesting showdown between the mathematicians and people who were involved in the computer project. The mathematicians didn't want the computer. They said, this isn't something that's going to be relevant to the future of mathematics. This is a nasty machine with all kinds of, all kinds of weird stuff going on in it. And when von Neumann died, a chap called Tom Watson kindly offered to send a truck from New York to come and collect the computer. And Tom Watson I think Tom Watson Jr., who was then the CEO of IBM. And so they took at least that's my the version of the story I heard. In fact, a friend of mine ended up getting the one thing that was left was the on-off switch for von Neumann's computer was bolted to the wall in this building. And this friend of mine, who's a trustee at the Institute, got when they were demolishing that building, he got the on-off switch for von Neumann's computer. So that's the version of the story I've heard, at least.
Right. Well, thanks. Let's move on. Thanks a lot.
Yeah. Thank you for this question. Thanks for the reaction. Next question, Max. Can I invite you?
Yes. Thank you very much, Steve, for a wonderful talk as well. I really enjoyed it. I have two questions, and I hope there is enough time for it. I'm not sure if we're going over time, but let's try to be short at the first one at least. So let's imagine that our universe is a huge simulation, as some people seem to think, like Nick Bostrom and Elon Musk. So now the question I have is if the person that needs to run the simulation could use a classical computer to run the simulation or a quantum computer to run the simulation. So people like Gerard het Hoofd, who I think was on the audience from at least before, have a sort of a classical view at the Planck level. So there's a cellular automaton that runs at the Planck level, and quantum mechanics emerges as a sort of like thermodynamics. Mm-hmm. Now, if I try to understand your theory about multi-way state graphs, does that imply that, in fact, the person that runs the simulation at the Planck level would have to run actually on a quantum computer to simulate the universe, or could she use a classical computer?
Okay, so let's untangle that a little bit. So when we simulate multi-way systems, we're using classical computers because that's all we have.
Of course. Yes.
And we can do that. There's no fundamental obstruction to doing that. Now, the parallelism that happens in a multi-way system is something that our classical computers can merely simulate. Now, one question is, okay, so is the multi-way system actually a quantum computer? How does it work? Well, we can actually say a lot about how quantum computing has to work, because as I mentioned, we can actually take quantum computing framework, compile it into multi-way systems and so on. But we have a very important piece that hasn't existed in the standard quantum computing kind of approach, which is we actually have a theory of measurement, a microscopic theory of measurement. We can actually say what has to happen to measure. So in typical quantum computer, you're imagining you've got all these parallel threads of computation that are going on, and that's what allows you to do things more quickly than a classical computer. But the problem is, and I've kind of known this problem since the beginning of the 80s, actually, that you parallelize by quantum mechanics, but then to make a measurement, you have to corral all those parallel threads back together to say a definite thing happened. We now have a model of corralling those threads back together. We haven't completely finished this, but it's looking very bad for quantum computing in the sense that it looks like the effort to corral the threads back together is more effort than it would take to do the classical computation. So in other words, that there isn't a fundamental advantage to quantum computing, at least at the theoretical level. Now, as a practical matter, the actual work people do on quantum computing is mostly concentrated on using different kinds of physics to do computing other than just semiconductors, and that's very valuable. But the question of whether you get the official, I'm a quantum computer and I can run Shor's algorithm, to do factoring in polynomial time and so on, that brand label probably isn't going to end up working out. But so now the question is, if you imagine the universe, so it gets very confused talking about modeling and computers and so on and so on and so on. Just to clear up one issue, which is sort of a philosophical issue, what do we mean by a model? We mean a representation of how a system behaves. We do not imagine, when we talk about a differential equation model of the motion of the Earth or something, we do not imagine that there are little copies of Mathematica running that differential equation somewhere inside the Earth. We merely imagine that differential equation is a representation of what the Earth does. And so similarly, the fact that our model is computational and can be talked about in computational terms does not mean it has to run on a computer. It's just a representation of how we think the world works. Now, if you say, well, could you run it on a computer? Well, sure, you could run any of these models on a computer. Could there be, could we be in the middle of a giant video game and this model is simply running on God's computer, so to speak? And are we somehow embedded in that system? Well, the answer is, what can we say about that hypothesis? So there are lots of problems with that hypothesis. I mean, among problems are, once you have this rule, you're either following the rule or you're not. If you're not following the rule, if you're following the rule, then there's no choice about the universe. It's just, the fact that it is in a simulation is not really relevant. The next question is, if you say, was the simulation, in order to say it's really a simulation, there's a puppet master. The puppet master has decided to make this universe. What does it mean that this rule was put there? You have to start talking about the rule was put there on purpose. How do you attribute purpose to this rule? Purpose is a deeply human kind of thing, and you can't really, it's hard to pull that back. And the final killer, as far as I'm concerned, is this whole rulal multi-way system story implies that it actually doesn't matter what the underlying rule is in some sense. And so in a sense, the video gamer who is, playing God, so to speak, for the universe doesn't have much to do. They just have to start the thing off and it's running some computational rule and there it's making our universe. So it's kind of I think I think I didn't do a particularly good job here. There's a slightly longer version of you can sort of untangle the argument. I think it is a philosophically sort of tangled and doomed idea. Okay. It's an interesting idea, but I think it's doomed. But any case, sorry, you said you had another.
Yeah, I did have a second question.
Well, let me intervene a little bit, because I think in view of the time, I would like to prefer to first go to the next speaker. Jan.
Okay.
Yeah, thanks. That was really wonderful and interesting and somewhat frustrating at points, because there are so many questions about details that I had that I would love to know the answer to. So maybe I'll just ask a generic question about the connection to physics and experiment at the end of the day. I was curious, so from a high energy physics point of view, if we look at the universe, we can ask questions like, well, what are the ingredients we can add to the universe that we know? We only know bits and pieces of our universe. What are the things that we can add to the current universe that are theoretically consistent as far as we can tell? Those extra ingredients may not actually be part of our universe, but they might be theoretically consistent. So there might be this zoo of theoretically consistent universes, and we might just happen to live in one. If that's the case, so this sometimes goes under the name of the landscape or the swampland program, you may have heard these words. If that's the case, then we might be looking for a needle in a haystack in order to precisely find that one particular set of rules that corresponds precisely to our universe, because we might just happen to stumble on another consistent universe.
Right, so first comment to make is about the nature of these kinds of models. So one thing that happens with mathematical equation type models is you end up with two types of things. You end up with sort of initial value type models where you say, here is a rule by which the thing operates. It may be a differential equation, maybe some field theory, whatever. Started off in this way, this is how it will develop. That's case number one. Case number two is more like the boundary value case, where you say, here's a set of constraints. Our universe is one of the things that satisfies these constraints. In these kind of computational models, we're very much pushed towards the first of these ideas, not the second one. In other words, in a computational model, you might say, well, we've got a bunch of constraints for how we lay down black and white tiles on a plane or something. Then we say, our model is those constraints. Now our universe is some set of tiles consistent with those constraints, as opposed to something like a cellular automaton, where we say, here's this rule, given this rule, grind, 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 this is what generates the universe. So there is much less of a tendency in these computational models to end up with something which is a constraint-based system of the kind that you end up with in things like the string landscape and so on. I mean, that's the fundamental sort of structure of science question. That's why that's happening, is because you get a set of constraints rather than a prescription for how the universe works. Now, in terms of you know, could we, okay, so an important point about what we're doing is, a lot of what we've done, okay, so we've studied a lot of very specific underlying rules and what they do. It's very hard to go from the specific underlying rule to work out the mass of the electron or something. We haven't been able to do that yet. We're not sure how hard that's going to be. What we have found, to our great surprise, is that there are generic features of these rules that don't depend on the precise details of each rule. It's the same kind of thing that happens in thermodynamics or hydrodynamics. You know, we can derive the Navier-Stokes equations even though we don't, you know, even though we can have different structures of molecules and so on. And so a lot of what we've done in deriving general relativity and deriving quantum mechanics is using that kind of idea, is a generic result independent of the precise details subject to some conditions about the underlying rule. Now you can ask the question, so that's kind of the, and you know, what we've discovered is that 20th century physics, the key things in 20th century physics seem to be generic to this class of models. Now, when you say, what about the particular particle masses? No, they're probably not generic. One thing that I have a suspicion about, we'll see, is the question is what's generic and what's not. So for example, we're looking at gauge invariance. We're looking at local, we think we know how local gauge invariance works in our models. The question, well, it's actually pretty nice. I mean, it's basically things are, you're seeing roughly the way that you get this limit of space-time, of the spatial hypergraph, you can get a similar limit about the way permutations work, and this bag of permutations limits to a Lie group. It's roughly what happens. Now, we don't yet know, we might know in a few months, whether, for example, you know, maybe it's the case that a subgroup of E8 is a generic feature of the gauge group for the universe. We don't know. Or it might be that we have no idea, that all we can say is it's a Lie group, we don't know which one. So we don't know what's generic and what's not. I'll be totally amazed if the electron-muon mass ratio is generic, but who knows? I mean, my guess is that's specific. My guess is you need to know the particular rule to be able to derive that.
Great.
And,
if I can quickly follow. So what do you think is the generic, did you discover, or do you think you might soon discover a generic feature in your models, which is a new ingredient of the universe that we did not know yet?
Yeah, I think so. I mean, I think we have, okay, so here's the issue. We have a bunch of phenomena that, and we're just in the process of inventory, that these models suggest might exist. Now you say, well, you know, let me turn my telescope on my particle accelerator in a particular direction. Can I see this? Well, that requires quite a lot of computation to figure that out. I mean, it's like, you know, given a theory of universal gravitation, what's the motion of the moon? That took 150 years to work out. It's hard to work out. What we're looking for right now are the soft targets of things where going from our models to an actual, you know, experimentally observable prediction is comparatively easy. There's one more problem, which is that, as I mentioned, we have two scales in the model. One is the speed of light. The other is the maximum entanglement speed. We don't know the maximum entanglement speed. If we knew the elementary length, which we think is much smaller than the Planck length, by the way, probably more like 10 to the minus 100 meters. If we knew the elementary, we only need one more scale. If we knew the elementary length, the elementary time, the elementary energy, the maximum entanglement speed, they're all connected. Once we have one of those, we have them all, but we don't know any of them. So there's an unknown parameter there. Now, do we have, you know, are there statements like for example, we have a guess that photons in orbit around black holes, that there will be correlations between photons in orbit around black holes that probe the connection between physical space and branchial space in a way that's different from any existing theory. Essentially, it's something that would arise from some theory of quantum gravity, but there's an implication for it from our models, but we don't know the details of that yet. Another thing I strongly suspect is that there may be dimension fluctuations in the universe, and that may be observable in features of the cosmic microwave background, and maybe some other things. Again, we don't know the details of that yet, partly because doing differential geometry outside of integer dimensions is really unknown. I mean, that's a thing comes out of our models. We can start seeing how that works, but that's not a known mathematical kind of thing. And so we have to, it's just hard work there. There also are things, I mean, it's conceivable that some of this maximum entanglement speed stuff might be visible in quantum computing type experiments. We're not sure yet. Another thing that is conceivable is that because of the length scales that seem to exist in our models, there is at least a suggestion that there's a whole zoo of particles much lighter than the electron, like 10 to the minus 20 electron volts, things like this. It doesn't have to be there in our model, but it seems likely. And that has implications for dark matter and things like this. That's another pile of consequences. I mean, there's lots of different pieces here. It's just a lot of work, which we're slowly, we and a lot of other people are getting involved in this, are starting to understand, how do we actually go to something which I think many of the things that we will come up with probably will be things where we say there may be this phenomenon that you never thought would be there, rather than we can say it will be 2.7 times this or something. But I'm not sure. I mean, Einstein was pretty lucky with the bending of light around the sun, because basically he had a scaleless prediction that it would just be a factor of 2 larger than the Newtonian theory. And that was amusingly, we have this potentially scaleless prediction about photons in orbit around black holes, which is a surprisingly similar case. But most of the predictions we might make will have a scale in them. And since we don't know this one underlying scale, we're kind of stuck on that. But it's hard work, and I think that the thing, there's kind of what we can do in experiments, and there's what our model says, and to what extent can we bring these two together? Because there's things that our model would say, if we were able, like for example, I just did a thing recently. I was curious about, could we go faster than the speed of light, right? Given that people say, if you go to a typical person, you say, I have a theory of physics, they'll say, is warp drive possible? Okay, so I decided I would try and answer that question. So the answer, I'm pretty sure, is that it is possible. But the way it works is the causal graph, there are these causal cones which work just the way you'd expect light cones to work. But the structure of space is more complicated. And so you end up with these sort of tiny space tunnels. And the issue is, it becomes a question more like thermodynamics. If you say, I've got a bunch of molecules bouncing around in this room, then I can ask the question, if I was sitting on one of those molecules, could I make choices about when the molecule collides with other molecules? If I could compute exactly what my trajectory is, I could pick things in a very careful way so that that molecule would just zip to the other side of the room without following diffusion. And essentially, I think you do the same kind of thing in space-time. It's something that it turns going faster than the speed of light from being a physics problem to being an engineering problem, but it's an engineering problem where you basically have to hack the structure of space-time to be able to do it. You have to be able to predict features that are happening at the elementary length to be able to do it. But it's sort of interesting to see, I mean, again, that's something which is a prediction of these models, that things like that should be possible. But if the elementary length is 10 to the minus 100 meters, it's going to be at least a while before we can detect that. Although, I was just seeing a couple of days ago somebody who has an experiment based on correlations between gravitational wave detectors that's able to potentially detect noise at Planck type scales. So, that gives one hope. I hadn't thought of that idea. It's a good idea of how to do that. There are probably other ideas like that that potentially allow one to probe this, but that's a lot of hard work that has to be done.
Great, thanks.
Okay.
By the way, I just want to say about string theory. I just want to make one comment about string theory, which is when I was trying to write up about this project, I was talking about these rewrite systems on strings, and I thought if I have a section of this thing about where the title has the word strings in it, people are going to be irreducibly confused because there's also string theory. And then I thought, what is the continuum limit of a string rewrite system? And I had this terrible realization that the pun might actually be physics. That is, that the continuum limit of a string rewrite system may actually correspond to string field theory. But we don't know that yet. I'm hoping somebody's going to work on that. But it'd just be fun that that pun becomes real. Okay, I'm sorry. I tend to. There's so much to say, and I tend to be quite enthusiastic about it.
Thank you for reflecting on all these things. I think there's one little question of Max. We still ask him to ask the question.
I'm seeing
your microphone.
Yes, I don't want to bet on the little part of my question,
Oh.
but so I can formulate it compactly, but I'm not sure you can formulate the answer compactly, but maybe we can try. So the question is, so I listened to one of your podcasts with Lex Friedman, and there you actually commented something very intriguing, is that the multi-way graph might actually have interesting implications for intelligence. And for maybe conscience. And sort of, I was wondering, is there a relationship, so consciousness, so is there a relationship with maybe sort of, so Roger Penrose also has this idea that, you know, intelligence or consciousness really needs to come from a quantum gravity theory and some kind. Of course, I don't know about it, but you seem to hint on something related. So can you expand a little bit on the relation of your theory?
I'll try and do this quickly.
Yeah.
So, you know, I have avoided for decades, when people ask me about consciousness, I've kind of avoided it because I've thought it's a very mushy, meaningless concept. And I kind of use the analogy of something like life. You know, you say, what's the abstract definition of life? Well, life on Earth, it's pretty easy to define because it's all kind of historically related. It's all got RNA molecules in it, et cetera, et cetera, et cetera. But life in general, what is it? Hard to define. Consciousness, we know what it is in us, but what is it in general? Can we say that there's something, you know, can we scientificize consciousness in a way that's more general than just the consciousness that we humans seem to experience, that is deeply tied into sort of the history of our culture and all this kind of thing? Okay, so I had for a long time just avoided the whole consciousness thing. But what this is the beginnings of so in these models, it's let's see how to explain this. The kind of, you have all these things happening that are sort of this whole computationally irreducible, you know, huge number of things that are happening at this very microscopic scale. But somehow that all has to be knitted together to be something that we can describe. So we could say there's 10 to the 400 points in the universe, and they're all doing their own thing, and it's very, very complicated. And we are just lost. We cannot predict anything. We have no story we can tell about what's happening in the universe. But the big fact about science is that it isn't that complicated, in the sense that we can actually have a narrative story to tell about how the universe works. We can take all of those details and we can somehow have a symbolic representation of at least certain aspects of those things, and we can turn it into something that we can describe and that our brains can process. And I think that the ability to do that, so it's not obvious in the abstract that that's going to be possible. It could be the case that the whole universe is computationally irreducible. There's nothing we can say. There's no predictability. There's no way we can have a narrative. We can have a way of thinking about the universe that is anything more than just the micro details of the universe. But in fact, we do have a way to sort of slice the universe so that we are able to describe it. And I'm kind of thinking, and I haven't worked this all the way through, I kind of think that that ability to take the universe and slice it so that we can talk about it at a higher level, that is some operational version of what we mean by consciousness when applied to things like physics. And by the way, what's important there is, okay, so there's a slightly technical thing that's kind of interesting, which is, okay, the question is, if you have two things that are equivalent, where you can say this state of the universe is equivalent to this other state, should we also consider them to be identical? If we see two things that are exactly equivalent, do we consider them identical? Okay, that question is a question that, you know, if you look at Euclid's common notions, for example, one of them is, you know, one of them has to do with if A equals B, B equals C, is A equal to C, these kinds of things. Under what circumstances are things which are equivalent identical? So that question so I have this suspicion that part of the story of how we manage to make sense of the world is that when the way we experience the world is such that things which are equivalent are considered by us identical. And that's important in these multi-way systems, for example, because the very fact that you can merge two branches of the multi-way system is a consequence of the fact that those two branches will lead to equivalent states. But the fact that we merge them means we're treating them as identical. And that also has a consequence in mathematics. It is related to the univalence axiom for homotopy type theory, the univalent foundations program of mathematics, this idea that that which is equivalent can be considered identical. Now, this notion that you have a thread of existence for which that which is equivalent can be considered identical, I think may have something to do with our perception of our sort of version of consciousness. Let me try and say that slightly differently. So the question is, it's a very difficult thing to imagine, because you've got this multi-way graph, it's branching, it's branching, it's branching. Many branches that it produces are identical, are equivalent, so to speak. But the question is, should we actually merge those branches? Well, we exist in this multi-way graph. So we and our brains and so on are themselves also branching in all these different ways. Many of those branches are equivalent. The question is the fact that we have this kind of thread of reality that we perceive, is that the thing that kind of defines the fact that we are considering these equivalent branches to be identical? These are difficult concepts, and I haven't cleaned them all the way through. But that's the basic. So I'm less pessimistic about my feeling that that sort of consciousness is a sort of extra scientific kind of concept, or that it's one that is purely historical, so to speak, that it's purely associated with our experience, so to speak. I think there may be a more abstract definition of what it means to be able to essentially to extract a symbolic representation of the universe, may be an additional feature of that thing we call consciousness, beyond what I think is a necessary feature, which is essentially computational sophistication. I think you don't get to have life, intelligence, consciousness without computational sophistication. Without that, it's, you know, one of the features of computational irreducibility is, you might say computational irreducibility is a big downer because it implies that there's so much we can't say in science. It also has a very positive thing to say, which is the elapsing of time actually means something. It could be the case that we lead our lives and you know, the answer is just 42. And we could, in a sense, just jump to the end without going through all those intermediate steps. But what computational irreducibility tells one is that, in a sense, those intermediate steps have significance, which wouldn't be the case without computational irreducibility. All right, I can go on. With respect to Roger Penrose's ideas about quantum gravity, I don't know. I've talked to him about those things a few times. I never, you know, it's always so difficult because Roger has many great ideas. I don't, at the present time, I don't think this is his best one. I think, but on the other hand, I've thought that, you know, one of the things that's really interesting is like our multi-way causal. I'd always thought twistor theory was kind of a weird, irrelevant thing, but it looks like our multi-way causal graph may be deeply related to twistor theory. So one can never be sure. I tend to operate on the principle that if people have thought of enough interesting things, one should listen to each new thing that they have to say. But this particular one doesn't seem like the best idea right now.
Thank you very much.
Okay, well, I think I say in view of the time, but I think we have spent the whole evening with you, Steve. Thank you very much for sharing so much of your time with us and so many splendid ideas. A lot of food for a lot of thinking here, and we are very happy you have spent so much time with us. I would like to thank all the members of the panel for their very thoughtful questions and all your very rich reactions to it. So this would be the moment to close this wonderful evening. And let me finally also thank the viewers, which have been, for their stimulating acts, I would almost say. But we had a lot of people sharing tonight. And so I really would like to thank all those people and that stamina, because there's still lots of people watching it. So again, thank you all for sharing all your thoughts and ideas, and in particular, Stephen. Thank you very much.
Great. Bye, everybody.
Thank you so much.
Bye-bye.
Thank you very much.
Bye.